us towards some definition of geometrical finiteness. Now that we have a boundary theory for any of these hyperbolic groups, there's kind of a natural question you might ask yourself. And this is just a general question that you might have about any group. So if you have a group and a subgroup with some notion of a boundary, is there a map? F, which takes boundary H to boundary G. And this is maybe the most general type of question you might ask, is there a map at all? But Hannah Thurston type question is, well, does the inclusion and subgroup inclusion extend continuously to an equivariant map of a boundary into the other one? And really, however you change this question will maybe tell you more about the group. Having a map at all might, maybe in some contexts, might tell you something about the subgroup H. But then if you put more restrictions on what the nature of this map can be, then you might be able to restrict the kind of classes of subgroups that you might be considering. What's more, yeah. And so the definition we want to look at is going to be kind of a pretty restricted class, but this will tell us nice things about our subgroup. So let H be subgroup of G, at least we're going to be, I want both of these guys to be HHG, so they both have boundaries. And we're going to call H a geometrically finite. Say H is geometrically finite. And G, if the inclusion map extends to an H equivariant embedding. I'm sorry. Of the boundary of H, the HHS boundary, HHG boundary, H is that of the boundary of G. This is a fairly restrictive condition. What it's telling you is that whatever this natural HHG structure you have is in some way compatible with the HHG structure of the ambient. Yeah. I guess. Nice. In my head, I wasn't listening to it. In my head, this is everyone's head, unfortunately. All right. So what's the? Thomas is going to pull the trapdoor in 7 minutes, I think. No, the main application of this notion is to mapping calculation. I'm going to take the subgroup H and I'm going to tell you 4 subgroups. One is mapping class of Y for any proper subsurface. 2, so-called convex co-compact. Subgroups. Finitely generated each. Subgroups. And 4, laminar read combination subgroups of these Veach subgroups. And the conclusion is that H is geometrically finite. few minutes to comment.
Sorry, what's number one?
Number one is mapping class group. There's an international ways to embed mapping class group of subservices.
What is that? I'm sorry.
Oh, I'm saying H is any of these things.
Ah, okay.
Okay, sorry. So if H is any of these subgroups, then it's geometrically finite in this sense. And in particular, these guys are all hyperbolic, and all their boundaries embed continuously and invariantly into the boundary of the mapping class. And we haven't, and Mark and I were just talking via email about this, but there certainly are lots of subgroups of the mapping class group where this is not true. Well, I mean, there are certainly lots of subgroups that are not hyperbolic subgroups of mapping class groups at all. So that's already restricting it down to a finer collection. But we think maybe that, haven't really thought this through, but or worked it out, but that the point pushing map subgroups are probably not. These are all hyperbolic, these are all surface subgroups, all surface groups. They're probably not.
Right. Right. They're normal.
Yeah.
Right.
Right.
That was the.
That was the reason.
Did I make it enough to count this and goes and whatever that would be?
That's a good question.
DG filling code.
Yeah. That's the right picture.
Yeah. Okay. I want to say a couple things about what these. For the first one, remember we were talking about these product regions. What a product region is a mapping cluster for one of these subservices. It looks like you have a bunch of different copies, and the whole product region is just foliated by these different copies. You just fix the complementary factor. I've already erased the things. You fix the complementary factor, and you have all these copies of these mapping clusters. And so you might expect that not only does the HHG structure work really nicely with the ambient HHG structure, but it's just giving you this really lower dimensional cut through it. So having it be geometrically finite should make some sense, but it's also not hyperbolic or anything like that. Whereas all these convex co-compact subgroups are hyperbolic. This is a really well-studied class of groups. Every subgroup of the mapping class group determines the surface group extension, and Farber and Moser showed these are precisely the subgroups that determine hyperbolic surface group extension. And they have lots of different characterizations. It's equivalent to being this convex compact is equivalent to QI embedding in a curve graph or having a quasi-convex orbit in Tycho-Moore space. And in fact, it's also equivalent to this stability notion that Matt mentioned, that Sam Taylor and I proved that. And that's a very restrictive convexity property. But already you can see that you have a QI embedded orbit in the curve graph, and that means that you're not really doing anything else in any other subsurface. And it just works out really nicely. These guys are examples of what are called hierarchically quasi-convex subgroups. And a hierarchically quasi-convex subgroup has some complicated definition, but really what you should think about it meaning is that there's a natural way to induce an HHS structure on this HHG structure on these subgroups, and it works really nicely with the natural ones that they have. These guys are not. Beach, I have 2 minutes, I think I can say this quickly. Beach subgroups are really nice punctured surface subgroups. They act on, they have, everyone determines a Tycho-Moore disk, which is an isometrically embedded copy of the hyperbolic plane inside a Tycho-Moore space, and they stabilize this nicely embedded copy. And these landing degree subgroup, but they're stored, their orbitals are stored in Tycho-Moore space, as are these landing degree subgroup combination subgroups of each subgroups. The really nice thing about these guys is that this is the thing that I'm going to read, is that there's this surface subgroup, closed subgroup of the mapping class group, such that all but one conjugacy class So these are as close to being purely pseudo-non-self subgroups that we have, and building purely pseudo-non-self subgroups is an interesting thing. And if you can prove that there exists a purely pseudo-non-self surface subgroup, then you can get everything else. But the point is that these have a lot of nice geometry in terms of the Teichmüller metric and in terms of the Teichmüller space, but they don't extend nicely to PML. So if you're trying to study subgroups and their boundaries in terms of Teichmüller space and PML, this isn't going to do it for you. But if you move to the context of the boundary of the mapping class group in this HHG setting, then you in fact do get a nice boundary. Okay. Thank you.
Questions for that?
Yeah.
So I understand that, the quasi-convex example, you can just sort of push the hierarchical hyperbolic structure to the subgroup.
Yeah.
But with these ones that you say are not, did they come along with their own structure?
Well, these are all hyperbolic.
Oh, I see.
Yeah, they're all hyperbolic. Sorry, I guess. I mean, so these are sort of. I said a bunch of stuff. I didn't write anything down. These are all hyperbolic. So what we're really saying here is the Durham boundaries of that. Sorry, that's a good point. It's a really good point. Yeah. What we can imagine is that they do interact with these product regions. They just cut through them diagonally. And hierarchical quasi-convexity says you can't do that. It should say that if you see a big slice of the product region, you should see all the directions there. You don't. Yeah.
Lambda y down there, did you mean lambda y in the boundary of S to G of y?
No, I meant the boundary of the curve graph.
Okay.
Of y.
But then are you saying you're tending to infinity in the curve graphs of all the subsurfaces then?
Pairwise Fishman subgroups?
Yeah.
Yeah.
But aren't there mapping classes? Like you could just do a pseudo-Anosov on this subsurface and leave this subsurface alone?
Well, I mean, those guys, if you look at the orbit of that, this
What is that?
compactification is going to tell you that you're going to converge to some point. It's going to tell you that you're going to have a subsequence which converges to this point. And so you get that subsequence which converges to lots of points.
Does that mean it's not Hausdorff?
It's how I'm confused.
If you have a topology where you have two sequences and converge to two different points?
Subsequence.
Oh, subsequences, sorry.
Yeah. So compactness allows you to make subsequential arguments. If anyone
We'll talk
wants to
about
learn
that.
about this HHG stuff, a really good trial by fire is the proof of compactness. Because you use it compactly.